Welcome to another episode of Don't Panic Geocacher. My name is Arjen and I go by Waterfan5 on the geocaching.com website. Today's topic is a very special topic. It is about the Going Caching pre-event T-shirt 2022. For those of you that don't know what it is, I will give some context at the beginning, and after that, since the event has now passed, I will give how the shirt can be solved and all the puzzles that were involved and that you had to do and how to solve them. With that, let me give you some context about what is this pre-event shirt and what is Going Caching. Going Caching is a mega event that nowadays is held in Rome, Georgia. For the last few years, it has been in that location. Before that, it was located in other locations inside Georgia. The key organizers of the event are geocachers known as the Waysiders, and together with the Going Caching crew, they organize a great event. The event always has a theme and lasts multiple days, from Wednesday to Sunday, and is very puzzle oriented. Not only does the pre-event shirt that I'm going to be talking about have a puzzle, but there are several other puzzles that you will need to can solve during the mega event itself. This year, the name is the Reign of Geopatra, and the event is Ancient Egypt. And people are dressing up for this event in the style of the theme, and a lot of the caches that are released are related to the theme, and there's a lot of other theme-related events that are going on. Each year, before the event, typically a few months before, they release a pre-event shirt. You can buy the shirt from their website, and the shirt itself has a puzzle. The idea behind the puzzle is that it gives you enough information on what to do on the day of the event. Puzzle is typically pretty difficult, pretty hard to solve, and so it's pretty elaborate what you have to do, but once you solve it, you should have information on what to do on the day of the event. Note that it never gives the exact cache coordinates or container coordinates, but typically it gives you meeting locations where you will receive more information, together with the time and the location of where to meet. In certain cases, it may also give a combination code, although they have also been distributed. This would be the lock on the container itself. So after you've solved the shirt and you know what to do, on the day of the event, you meet up at the designed location, and then you find out further instructions, and at that point it becomes a race who can find the geocache, who's the first to find on the geocache, and the winner gets a cash prize. So with that, let's talk a little bit about this year's, the 2022 t-shirt. So important is always that the shirt doesn't come just by itself. It typically comes with some other information. In past years, it could have been an entire puzzle box. We've also seen just some letters being included. And this year there's a variety of pieces. And if you evaluate the content, then you will find a opening letter, which is Rosetta University letter, of course the shirt itself, a business card, a brown letter with hieroglyphs and notes, referred to later on as the garment, a subset of the American Nautical Almanac, plus a worksheet, and of course all of this was inside an envelope, together with a scarab charm. Also included here were the order letter with your address information, showing what you paid and where it was shipped to, as well as a square note on how to support the Going Caching 2022. Why do I list all of this? Because typically everything that you receive might be involved in the puzzle. Nothing is excluded, and you shouldn't overlook anything that you receive. So you see here some quick samples of the information that was provided. The letter, the garment, the back of the shirt, the almanac, the envelope, the charm, the business card, as well as the support letter. Now note that the order letter and the square note didn't seem to have any of the puzzle content here, but that doesn't mean that you don't have to analyze them and see if there's any clues on there or any other information. It's always good to inspect them. So with that, let's take a look at the first part and the first element. Let's take a look at the letter itself. The letter itself. So here you see the letter that is included with the package. But the letter should be thoroughly analyzed, and if you do that, you will find a variety of clues that will help you solve puzzle of the shirt. Now, the first thing that you notice is the Rosetta University, founded in 1799 in the logo at the top. It's clearly a fictional university, but Googling the university wouldn't be a bad thing, because of course, in case you didn't know, uh, Rosetta Stone is a key element in translation that was found in 1799. And this stone helped with translating hieroglyphs. By having the stone having multiple languages included, people were using languages that they know, and now we're able to figure out how hieroglyphs should be read and how they should be interpreted. So this is clearly a hint to what we may have to do later. It also sets a timeline, so in this case we're set in 1922, and it includes some of the key stakeholders like Oleander, Fitzgerald and Dinkelmeyer. There's other people also involved and described here in the letter. It also talks about some of the terminology that will be used here in the package. So it talks about hieroglyphs, a garment, the almanac, a charm, a business card. It's good to remember these words because they may come up later on when you're working on the puzzle, give you specific things to look for. It also mentions that there was a strange glow coming from the package. So in our case, the package was the envelope. So maybe, and it is in this case, this is a hint as well that we maybe have to analyze the envelope a little bit further. And finally, just something to note. If you received an early version of the letter, if you were one of the early buyers, it may say Fitzpatrick as well as the name. And you see that on this version of the letter. You see at the top, you see Fitzgerald, and at the bottom, you see Fitzpatrick. In later versions of the letter, that has been corrected, and they both say Fitzgerald. So this is not relevant for the puzzle itself, but may throw you off when looking at it. So that is just some key pieces of information, just gives you some context to what you're doing later on and sets the story. One important piece to note is during the event there's typically a play as well, and the play typically features the characters that were also mentioned throughout the event and maybe throughout some of the puzzles, including the pre-event puzzle. So now that we have looked at the opening letter, it might be good to start looking at the first item. And I will start with the shirt and give you a little bit about information about the shirt, but then tell you how to do step 1 of the puzzle, and that is decoding the shirt. So here you see the front and the back of the shirt. And if we analyze the front, we'll have the usual information of the date of the event, the name, where it's located, and of course the GC code. But the picture itself also reveals a couple of important pieces of information that are hints to what we later on might be able to use. For example, it features a sextant here with somebody looking through it, and it also looks here at stars. Other years, the front of the puzzle may have had also certain codes on there. This year, if they were there, I didn't find them and don't think I needed them. So nothing on the front. The back of the shirt, however, as you can see, clearly has a set of hieroglyphs on there. Note that these were standard hieroglyphs, so not like following any standard module. So if you would search the different characters, you wouldn't find them in any of any specific meaning that would be useful to us here. However, there's also an English text on here. And this is where the first aha moment comes into play. Because as you may remember, I talked in the beginning, I talked about how the letter contains hints. Well, one of the hints was the Rosetta Stone, right? Where the same stone contained multiple pieces of languages. This puzzle does exactly the same. The shirt has the hieroglyphs and has the English text. And the aha moment that you need to have here is that the hieroglyphs and the text spell the same. It's quite easy to see if you look at it in more detail. And so let's do that and let's take a more advanced look. So we have here the text starts with Hotep, High Priestess. So there's twice an H in there. Now hieroglyphs are read as columns. So you read it from the top and then go down and then go to the column on the right. And it's also phonetic language. So those are two things that you need to know about hieroglyphs that are important and help you decode. And so they both start with an H, and you see here the same symbol starts with the same word. Another one is the first word ends with a P, and we see the little snake symbol. And then we see, for example, that the third word starts with a P, and we see the little snake symbol here. So clearly, this is going to be the same text as that we see right here. So now it gives us a way to translate the hieroglyphs into characters. And that's what I've done here on the next slide. I have for every character that appears, I've put the corresponding letter or sound on there. So sometimes it's just a single letter like an H, and sometimes it's multiple letters like A, Y, for example here. Note that these are the characters I associated with it, of how I felt that I could easily remember how it sounded to me. As you can hear, I'm not the best English speaker, so for you it might sound slightly different. This was just for me the clear interpretation of how I would know and how I would find which word it was, because it was all written phonetically. So you see, for example, here that in the text it says High Priestess, but in the hieroglyphics it only has the letter H and Y. And we see another word with, for example, temple, while it's here, as you pronounce it, T-E-M-P-E-L. And so you will see also that sometimes there's multiple variants for the same letter. So we see here 2 for the letter E, because they are pronounced slightly different. And so if you do that, you basically now know for a lot of the characters what they sound like. So you see a variety of characters here, but again, you see, for example, there's multiple E's. Some of them have double letters. TH has its own, and actually TH has multiple depending on where it's used in the sentence. So you will get more than 26 characters that you need to do, but at the end, if you do that, you kind of have a translation table that says this hieroglyph now means this sound. And this is of course useful when we try to look at the garment. So the garment itself has also a lot of text on it, but here, unlike the other text, we don't know what it means. So now we'll have to basically use the code that we have received from the previous one, and you see here the translation table. We now have to do that for this garment as well and see what text we get. But now, of course, in a disadvantage because we don't know the English text, so we kind of have to decode it one by one. And we see that, for example, here it starts with the 2 owls, and the 2 owls is the D, and then it has a man bending over, that is so deer is the first word. And so we can go through that one by one and get an entire decoded text. Pretty soon as we will do this, we'll find that we run into an issue as well. And you see several of the characters here that are listed here. I have a blank because they didn't exist on the shirt. So we don't know what sound they have until we know what word they're in, and we can decode the entire word. So let's take a look at the translation, and we see that right here. So we see here the entire text, and I will try to read it out loud what the text here says. So it says, Dear Professor Fitz. Remember the Professor Fitzgerald? So that's clearly a letter to him. It also ends with the word Lars, so it's Lars writing the information, something that was already kind of revealed in the opening letter as well. Now we have the first letter, and I marked them here as green question marks, that we don't know. So we don't technically know what this word is yet. So if this is R, reading this, again, the same word as that we see here, question mark and a U, and it's the same symbol right here. Might be a little bit hard to see here, but if you have the shirt or the event box, then you can follow along. And then realize, so we see here 2 variants of E, a long one and E, and that's basically this one almost like so realize. And then magnitude, so here we kind of get an extra letter because this is again the same symbol. So this is like kind of like a Y or a J. So here, if we do that in here, we now go U, and so now we have an extra letter translated that we didn't know before, and we now know that this is the letter Y, or a Y sound. You realize the magnitude of this. Well, it's a little bit of puzzling. It will say astonishing discovery. Can something interpret glyphs, something that we don't know. Garment, so this was why it was important that we recognize the symbols or the terminology, the vocabulary, so that made it easy to see. This was the word garment. With translation, again a word we don't know. Ongoing. Excavation, and then in Rome. So and so on. So it goes on, right? But basically, at some point, we'll find letters that we don't know yet, and sometimes we may have to puzzle a little bit what the word means. So, for example, here, visit. So, of course, it's here with an F because it's a V and an F is the same here as the sound. Visit of 2. And then this is the word millennia. So that took me a second to decode that. Millennia ago. And now by now we see the same word here, and we now have had it 3 times, here and here. This is now so we now know this is OW because this says now. So can now interpret. And so we now have an extra letter. And the same here, we have the letter here, which ends up being the word during. So we now know that the wormy character that is right here is the letter U, or is the sound U, and so on. So basically, by having the text, you can kind of fill in the missing letters and figure out what the missing sounds are that you need. That all works well until at some point in the puzzle, you end up at a certain words that don't really look like English. And so let me go a little bit more in detail before I give the final text of the shirt. So at some point when we start translating, you see here, you see a word with a question mark in it and something that looks like dobby and then nonki or nunki. So before that, it talks about a well-guarded, and now it talks about sextant and shot. So we know, of course, is the Y sound. This is the same sitting character. So we now know all the characters. And so we know this is the Y sound. And so this one says used sextant to shoot. And then it gives 3 names. Well, if you're not familiar with those names, they look kind of weird. And so it doesn't look like English and you may get stuck in the translation. Of course, you can translate the rest and it will talk about things that we need to know. I'll explain that in a second. So we have these words. And Aries, dobby, and nunki. That is the translation of the sounds that we got because they were used multiple times. And so you can kind of figure out. That may not mean anything to you. However, we also got a nautical almanac. And if you take a look at that, you will find a page that actually lists a series of stars. And if we zoom in to the specific stars, we actually see 3 stars mentioned. So, and these are the 3 stars that are mentioned in the text. Basically, in the text, he describes that he shot the location using these 3 stars. And that will be important for the next part of the shirt. So now take a look at the entire text. If you now decode it all, this is the text that it says. So, dear Professor Fitz, I already mentioned that, found garment, hits translation during ongoing excavation in Rome, surmised it was left during Geopatra's visit over 2 millennia ago, and so talks about now translating a series of glyphs on the tapestry, which may lead to some sort of treasure. This is going to be important, right? Because he talks about a series of glyphs and that they lead to some kind of treasure. We're looking for a treasure. He talks about a treasure. This clearly is aligned, right? It is secured and well guarded. Okay, that might be a hint about the final location. Used sextant to shot, and here is the 3 stars that he talked about, and Aries, Dubby, and Nunki, to mark location. Need your help to move on. Be there October 1st, 9:30 a.m., and the tapestry will be revealed. So he says he hit the tapestry somewhere, and we need to go find the tapestry, and it can be found at the day of the event, October 1st at 9:30 a.m., at the location marked by these stars. Now, I didn't really show it at the beginning, but this garment also had a second piece, and it had coordinates, or at least it had star locations on there. And that's going to be a future part of the puzzle. However, before that, we're first going to look at something else, because with the information that we learned about the hieroglyphs, we can now do a second part of the puzzle, the envelope. So when receiving the package, it's always good to look at every element of the package itself. And that includes the wrapping, extra notes, anything that you may find. It's also a good idea to look at everything with a UV light. And in this case, we got a note in the opening letter talking about a glow from the package. Well, that certainly means that we have to give the envelope another look. And when you put an UV light on the inside of the envelope, you will actually see these symbols being displayed. And now that we have decoded the symbols, we can actually translate what this says. So this was the K and this was the O, and so if you translate all of this, it will say combination keyword. And we have 6 different dashes here, so that means that we're probably looking for a 6-letter word. We also now know what the letters mean, right, from the shirt and the garment. So we're looking for a 6-letter word that uses a combination of these sounds. Of course, there's lots of sounds available, and since this is recorded before the event, we're not quite sure yet what word will be, but we have a good guess. And that guess is based on this little charm that we received, the scarab charm. This is a standard charm, but the word scarab is actually 6 letters, and also uses exactly 6 of these codes, because SKARAB. And so we can make the word scarab, and if we do that, the math actually works out. Now we're not 100% sure which ones are being used, but the first one was truly the long scarab. So it could be that it is 418683 or any of the other 2 combinations if the elephant or the scarab itself was used. And if we try to put that in the math equation here at the bottom, it all seems to work out nicely. 4 minus 1 is 3, 8 minus 6 is 2, and then either 8 plus 3, or 2 plus 3, or 5 plus 3, depending on which combination is used. And so now if we do that, we get either 3211, 325, or 328. Since we're probably talking about a 4-digit combination lock, the best guess here is the 3211, and we're guessing that that is the combination lock that is being used here. So now for the fun part of the calculations, the nautical almanac. This is the part where we now have to use all the information that we've learned and get to a location. I'll give some resources later on of where I got the information on how to do this, and so that you can look up the information itself, and I will try to explain some of the key concepts, but there is a lot more resources and better resources out there on the internet to explain this. So the garment mentioned, of course, this text that used sextants to shot Antares, Dubi, and Nunki to mark location, and then it has the date information and the times on there with the sextant readings. So we have October 1921, October the 1st. We have the 3 times of when they were shot in EST. This will become important. We have the 3 readings. We have the 3 stars, and it mentions artificial horizon. I'll explain that a little bit because that is a key part of the information that you need here. So a little bit how the concept behind celestial navigation is, if you have readings with a sextant, then you kind of say, this is what I observe, right then and right there. You compare that to your almanac. So that is the almanac gives you kind of like what calculated where, based on what you're telling where it should be. And then the difference gives you an intersect length and the azimuth angle based on which you can do a line of sight or a line of which is basically the 90-degree variation of that. And where the 3 come together is a close point of roughly where you should be within your error margin, right? Because we're always dealing with a certain error margin. So you try to get the points as close together as possible, but you're still always within a certain error margin, and you just don't want to make the error margin any bigger. than necessary. So that is the concept, and that's what we need to calculate. So we need to calculate the observed, to calculate the difference, and then we kind of have to measure out the intersection between the three areas. So just to give that a little bit more clarity, so if you basically look up in the sky, so then you will see where the different stars are. So that is basically if you rotate around, so that is kind of like the circle, and then how high it is basically the angle which you measure with the sextant. And so here this is taken Rome at roughly the time that it was measured, right, at the right date, and then you see the location of the three stars. So this was at 7 o'clock, and of course the times were at 7:06, 7:26, and 7:44. So this map will look different at those different times, but roughly they will be around here. Once you do that, there's a variety of ways, but you basically get the three intersects. Those are the three lines, and you take the 90-degree, and where they intersect is where you end up. Note, this is not the final location. This is just an example of where this is, of what it would look like and what you have to do. So moving on. This was the worksheet that was provided, and this is actually a key element because when you do celestial navigation, there's lots of steps that you can do. There's some optional steps that you can do. There is some variations that you can do. And so this actually proved quite helpful to, for example, say, should I do this or should I not do a certain step? There's certain steps to get more or less precision. And this gave you a good guideline of, yes, I need to do this step. No, I don't need to do that step. So as you see, mine was well loved. And so I copied each section out and put it into a more readable format as well. But use basically this work spreadsheet. So we're going to focus on section 1 first, which is basically all about the observed altitude. So that is the first section that we need to complete. And we'll just start at the top where we fill in the different bodies, right? The three different star names, and each will get their own column. And so those, of course, we got from the garment again. They told us the star names. So next part we got as well. We can just copy that information. So that's the 36 degrees and 49.6 arc minutes. So we just fill in that, and that is the sextant altitude. And then we get the index correction. Well, for this, we needed the business card. This is what the business card told us. So this one told us where the instrument was bought, and it tells us 1.2 off the arc. And the off the arc part is important because if it's off the arc, we need to add. If it's on the arc, we need to subtract from what we measure. It basically is how well was the thing made. It's almost never zero. You can align it and can figure out once you measure it how well it's adjusted. And so basically you need to take that into account because this matters. It's big enough that it makes an impact. So of course, for all three measurements, that is exactly the same, right? It's plus 1.2. Now the next one is a very key part of this, and that is height of eye of artificial horizon correction. And I'll be honest, this threw me for a loop for a while because I had noticed that the numbers were twice as high as I expected, but I couldn't explain why. And it wasn't until I read more about artificial horizon that I understood what was going on. So again, it mentioned artificial horizon here. So that is what we need to fill in here, that we just use artificial horizon. That basically makes our height of eye correction 0. And here is how that is explained. When you're not at sea level, you don't really know your height of eye. You don't know how high you are above the horizon, sea level, and so it's kind of hard to say what your angles would be or what your adjustment would be. So a trick that you can use is something called artificial horizon, where you say, instead of doing the measurements directly from the horizon to the star or body that I'm measuring it reflected in some water, and the water will always be then flat, right? Because that's why then it evens out. However, that doubles all your angles. So instead of doing the flat line and going up, you're now measuring it compared to the reflection in the water. And that is now twice as high, because basically, since this one is parallel to this line, the reflection will be then parallel to it as well. So this degree is the same as this degree, which is the same as this degree, which is the same as this degree. So you get a number that is twice as high. But since you're measuring in this plate and since you have adjusted it, there is no height of eye correction anymore. You just need to divide your numbers by 2. So that explained why the numbers were all very big, and if you didn't make that adjustment, you would basically never get anywhere close to Rome if it intercepted at all. So that was the next part that you then have to do, is to basically say, okay, I have the altitude, I have my correction, and I have to divide it by 2, and that will now give me my apparent altitude. And you see those numbers here. Note that we're all dealing with arc minutes and nautical miles, so it's all 60 minutes in a degree. So we need to make sure that we do that if that becomes relevant in any of our calculations, right? So if we add 1.2, if we reach 60, then we go up by a degree. So yeah, basically 49.6 plus 1.2 is 50.8, divided by 2 is 25.4, and of course 36 is then 18. And the same for the other two, right? So you have to again add the 1.2 and then divide by 2. Add 1.2 and then divide by 2. And so on. So now we have the apparent altitude. There's one more correction that you have to make. There could be multiple that you have to make, but the spreadsheet only here, the worksheet says to only make one, and that is the altitude correction. And this has to do with the fact that when light comes in through the sky, the closer it is to the horizon, the more the light breaks, and you need to correct for that. You can take that from the spreadsheet, from the sheets, and I called it page 16, but it is the page that basically talks about the altitude corrections. And if you now read up the what you have as the apparent altitude, then you will find those numbers, right? So here it says 1825.4, so that is in between those numbers, and that gives me minus 2.9. Technically, you could get a slightly more exact number, but since our precision is only 1 digit after the dot, so 0.10th, we are not going to make further precision. And the same for the other one, 1522.6. So you see that right here. It's right in the middle here, so that is the minus 3.5, and the last one is 2814.1, which is right in the middle of this one, and so that's minus 1.8. So that is the 3 numbers that we need, and again we get that from this table on the altitude correction page. So we filled that in our table, and now we basically add, but since this is a negative number, it will at the end become subtract, and that will then give us the final number that we need here for this spreadsheet. So if you do 25.4 minus 2.9 is 22.5, this one minus 3.5 is 19.1, and minus 1.8 is 12.3, and that is our observed altitude. And this one we'll need later on, so this is an important number because we need that for our intercept correction. We need to get this number again. So this is an important key number. That is step 1 of the calculations. So now let's take a look at step 2. So here is the sheet again. So now looking at section 2 about the GMT time and date. So we have the different bodies, and on the garment it mentions the different dates, time and minutes that it was shot, and we just filled it in, and we note the time zone here as an EST. So this is important. I think officially they would be at this date in EDT, but since the time are marked here as EST, we're going to use EST as calculations. And we're doing an assumed latitude and longitude. And I'm just taking the whole numbers here because everything else we have to ignore later anyway. So we just need to know the right degrees. So north 34, west 85. And basically I took that from the caching page, just saying, expecting that that would be close to the final location. And now the final step that we need to do is the part where we have to calculate it back to Greenwich Mean Time, because that's what the nautical almanac works in. So in this case, EST is basically 5 hours behind. So we have to add 5, which puts us just above midnight at GMT time, but of course on the next day, October the 2nd. And this will again be important information that we're going to use later on. So back to our worksheet, we've done the first 2 sections. We're going to section 3, which is the local hour angle and declination. There's 2 ways to calculate this. In this case, of course, since we provided the almanac, we're going to use the almanac to do that. You could technically also use some math formulas to calculate a lot of the same things and only look up minimal information. But let's just go and take a look one by one what we have to do. So the first thing that we have to know is what is called the local hour angle of Aries. So that is the first thing that we have to look up. So for this we need the time in GMT. The whole almanac is in GMT. And we have to look at the table for Aries, because that is what we're going to compare it with. And I'll explain that in a second. And now we need to look up the hour, which is basically 12, so just midnight, right, at October the 2nd. So if we do that, if we zoom into that area, you basically can read that under the second column, the Aries column, it says 1108.5. And since all 3 are within the same hour, that is the same number for all 3 of them. That is where Aries is located. So we filled it in our table. However, since it moves very rapidly, we need not to know by the hour, but we actually need to know it by the minute and the second for the precision that is needed here. So that is called the GHA increment, the Greenwich hour angle increment. And so we're going to do that within the information, and we're looking that up in the nautical almanac as well. We need to do that 3 times, since all of them were shot at a slightly different minute and a slightly different second. So you see 6:53 a.m. So we need the page that has the 6 and the 7 minute increment and correction table. And of course, we need to look up Aries, so that is the second column. And if I zoom in a little bit, then we need to find the right minute, right? So this is 6 minutes and 53 seconds. And we found for Aries 1:43.5. And we need to do the same thing for the 25 and 10 seconds and 44:51 seconds. Of course, we need to look those up at the 25-minute page and the 44-minute page. So once we do that, we get 3 numbers, basically the 143.5 for the first one, and 618.5 and 1114.6. That is now the exact location of Aries for the hour, which we calculated first, and then the adjustments that we have to make for the minutes and seconds. So we fill that in the table. But Aries was not the one we were shooting, right? That was not the one we were looking at. We were looking at different stars. And so we need to find the location of the star relative to the Aries. And that's called the sidereal hour angle and the declination. So to explain that, if this is where the meridian of Aries is, then the sidereal hour angle is basically how far is it horizontal. That is called the sidereal hour angle. And the declination is how far is it up or how far is it down on the horizon compared. So basically it's either something north or it's something south that we're looking at. So that is the declination that we need to look at. And so we need those 2 numbers, and those 2 numbers come from the tables as well. So if we go to page 4 again, that we were on earlier, and this is the same table where we looked up the stars. We can find the 3 stars and we can find the 2 pieces of information. So which is what you see here for Aries, 112, 23.7, and the declination is 26 degrees, 27.9 south, right? So on the south side, 2b is north, and this one is south again. So we take that information from the tables, and we're going to put that into our spreadsheet or in our worksheet, right? So we put in these angles for the different, and we copy the declination in. Even though it says it later to do that, since we're looking it up right now, we may as well fill it in right away. So great. So we know where Aries is in the hour, we know where it was the adjustment we had to make for the minute, and we know the adjustment that we have to make for the body that we're looking at. So that means that we can now calculate where that body was in Greenwich hour, in Greenwich time, right? GMT. So basically we just add these 3 numbers together. Note that of course we're still working with arc minutes, so 60 per degree. So if we get across 60, we have to add the information, right? So 5, 5, and 7, 17. So 9, 43, and 23 adds up to 75. So that is 15. And then we have to add 1 here. So that is now 12, 1, and 112 is 125. Right? So it doesn't go to 100, it only goes to 60. So we do that for this one, and we do that for all 3, right? So we get the same information right here, and that will give us 211, 16.7, and the final one, again, you can do the math here. So we get 98, 18.7. Now we have to add or minus 360 if needed, but since we're at 85 west, we know that we're not going to add up at negative numbers. So we don't need to, these are all within the range that they would give us a good number. So we're not going to add 360. They're all higher than 85 west. So now we have to do kind of like a, I wouldn't say really a trick, but just something that you need to be aware of. The assumed longitude we can adjust because that is just for the mapping. And so we can deal with that in the mapping. However, in the almanac to look up something, the almanac does only give us whole numbers. So we need to have the local hour angle be a whole number. And we adjust the longitude to basically for the correction. So in this case, because we're going to subtract, because it's west, we're just copying the minutes. So the 15.7, and we copy that to the longitude, and that the 85 was our assumed longitude at the beginning, right? That was the 85. So you see that here, but we now have 3 different assumed longitudes because we want to get to a whole number. So we're just taking that across. If it was on the eastern side, it would be slightly more work because now we have to add, so now we have to do the difference to get to a whole number. But since it's on the west side, it's easy. We just can copy the same number across and use our assumed longitude, which is 85. Because now that means that if we subtract these 2 from each other, we get a nice even number. And that is 40, because 125, 15.7 minus 85, 15.7 gives 40. And this one gives 126, because 126 plus 85 is 2011. And this even each other out. And the same here, the difference is 13. So we want whole numbers because the almanac only thinks in whole numbers here. This is where we can do the first part of verification as well, because we were only given certain pages for local hour angles. So if you calculated this wrong, you wouldn't find the page, because we had a page for 40. You will see we have a page for 126 and we have a page for 13. So this is the first verification that we are on the right track. Declination we already filled in before, and the assumed longitude doesn't change, it's just 34 flat. We don't need to adjust that. Again, we need a whole number because the almanac only deals in whole numbers. So that gives us this part of that calculation where we have now calculated the whole section of where the calculated part is. So now we're going to look at the difference between the two, and that is again the next part of the worksheet. So the next thing we're going to do is fill in section 4. So section 4 is calculation of the intercept and the azimuth. So based on the observed altitude that we've already got, and now we're going to do the calculated altitude, which we're going to do as well. And we're going to use that information to get the final intercept and azimuth before we can start plotting all that information. So first part is pretty straightforward. We're copying what we already put on the worksheet before, and we're only taking the increment of the declination. So above we had looked up the inclination. We're only using the increment of that of the declination, and we're putting that in the table. The next step is that we have to start looking up information from the table, which is the interpolation factor, the computed altitude, and the azimuth angle. All of that is received from the tables. So we're going to do it first for Aries, and we need a specific page that matches the following criteria. It needs to be for the LHA, the local hour angle, needs to be 40, so we need that one. But also because north and south are contrary, the page also needs to say contrary. So we see that right here. And in that, we're going to look up the right information. So we have the right table, we have contrary, and now we basically need column for the 34. And so here again, we see we need whole numbers, otherwise we couldn't be able to look it up in this table. And we basically go to the row that has the whole number of the declination. So we see that right here, that would meet right there, and if we zoom into that, we'll find the numbers, 1900.4, that is the total. The next one is the increment, and the last one is the azimuth. So we're going to put all three pieces of information in our table. But before we do that, we have to look up the same for the other two. So I'll give one more example, in this case for Duby. So here, we now need the page with 126. And of course, we need again the north 34. And in this case, because it's both north and north, we need the page that says the same. Now you see at the top of the page it says contrary, but at the bottom of the page it says same and it says 126. So if we look up that information and we do the same thing, we're going to the row for 34 and the column for the whole number 61. Then we get this information, and now we can copy again the three pieces of information. And so we have the 43.2 for the increment, the 1438.7 for the computed altitude, and the azimuth being 23.5. We do the same thing for the other one. Again, this is a contrary one, but now it's 13, and we're looking up 26 and 34, right? So that's how we got the last one, and you should get these numbers. And we put that in the table. So we put the first one over here as part of the interpolation factor. We put the computed altitude right here, and the last one was the azimuth angle that we found from the table. Now we're not going to further refine the azimuth angle. That was not the exercise, otherwise it would have said interpolate azimuth angle. It didn't say that, so we're going to skip that step here. Now we have to calculate the total correction, because the declination wasn't exactly a whole number, and that's why we needed the increment. And basically what we do is we calculate the increment, which is in arc minutes, so that's we'd have to divide it by 60, and then multiply it times the interpolation factor, which we got from the table, and that gives us minus 23, and we'll round that to minus 23.1. We do the same with the other two. So we have here 39.6, and we multiply that by 43.2, we get 28.5 rounded. And the same for the last one, we get 16.4. We multiply times the minus 58.7, and we get minus 60.0. So with this information, we can get the exact calculated altitude. Basically, we just subtract the numbers, and again, you have to think it's 60 minutes in a degree. So we do this number minus 60 gives us 37.3. In this case, it's plus because it's a positive number. Since we go above 60, it is 1507.2, so the degree goes up by 1. And finally, the last one again is a subtraction, and so we end up at 2828.7. So now we have the computed altitude. Now the formula says that we have to subtract the two numbers. So we can copy across the observed altitude that we had calculated earlier. That was what was measured with the sextant, and we calculate the difference, and that is our intercept. Now the intercept could be a positive or a negative number. So you see here it's a negative number, and that will means that we'll have to do something special with the azimuth later on. So same here, by subtracting the two, we get the minus 14.8. Same here, but here you see that it is a positive number. So, and the last one is again a negative number, since the computed one is higher than the observed one. So that gives us basically how far off the error or the offset is that we need to work with, and then we'll work with the angle of it. So what we're going to do with the azimuth now is going to calculate the true one based on where we are and based on whether this is a positive or a negative number. And that is the final step here that we'll have to do. So now we'll say, okay, we're on the north side. So this is a north. So in that case, the formula is 360 minus the azimuth angle. For the south, it would be different. And for negative numbers, we also have to subtract 180. So if the number is negative, because we're basically going in the opposite direction. That's what the negative means. So we'll then get these three numbers, 37.4, 336.5, and 13.3. So it's just very basic math in this case. Note that we now have all the information we need, and we can start doing our plotting. So now we're going to plot the information, and this is the information that we need. Of course, the three bodies and the assumed latitude and longitude for the plotting purposes. So we copy those from section 3. So this is 33.0, and for all three that was the same. And the longitude had a slight difference between the three of them because of the calculations that we had done. For the intercept, we're using the absolute value, so we don't use the negative anymore because the negative was taken into account when we calculated the azimuth. So we no longer have to use the negative number, because if it was against, we did the minus 180. And this is the information that we need, and with this information we can now start plotting. So let's do our projections. So we're going to map out using the information that we gathered from the worksheet, and we're going to plot those locations and see where they are on our map and see if they nicely intersect in a perfect location. So this is the first one, which we got from the paper, and we use GPS format, so we say 3 digits. And we're going to use the same for the other two. Going to fill those in, and that is the 3 assumed coordinates that we have. And we see them plotted right next to each other because only the west, the longitude, is different. And we are ending up below south of Rome, but that is not an issue because the intercept and the azimuth are calculated for this location, and they should bring us back to Rome, where we expect the intersection between the 3 points will be. So the next thing that we're going to do is we're going to draw those on the map. So again, we're taking the numbers. So for the first one, it's 14.8 and 37.4. And we'll see that is the other way around. So let's try to reverse that. So because it was the angle was 39 and the distance was 14.8, that looks a lot better. However, it's still not correct because we need to use nautical miles, right? Not regular miles, because it's arc minutes, which is the same as nautical miles. And we see the line is slightly longer, and that is the first line. And we're going to do the same for the other two. Fill in information there. So the bearing is 336.5 and the distance is 11.9. And for the third one, it is the angle is 13.3 and the distance is of the intercept is 16.4. So now we have the three lines, and now we need to intersect the 90-degree angles of those, which is basically the lines of where we need to go, and where they the intersection of those three lines is where we have our estimate location. So let's do that next. So we'll first take the projection. Now the projections are actually calculated here, so we can see those right here. The tool will automatically calculate them for us. So we take the first one, which is located right here, and we have a variable that we can use saying this equals the projection of the first point that we have. And in this case, we need to say 90 degrees off. Also for this, we can use a variable, and we say it needs to be the 90 degrees that is smaller, right? We can go in two directions. So we want here the one that's smaller than the angle. And you see that nicely goes towards Rome. However, that goes way too far, so we need to shorten it a little bit. So let's say 8, and 8 will bring us nicely into Rome. We'll do the same for the other two. So this one, of course, is equal to the projection of number 2. So write this one, but this one looks like it's bigger. So we're going to say it's a plus 90 that we have to do, but also this looks like a slightly longer distance. So we'll take 12 nautical miles here. And so, yep, this nicely have an intersection, so that's good. And we'll do the same for the last point, which is the projection of number 3. And also that one looks like we have to do plus 90. And this one is fairly short. So let's do it only 4. I think that looks like it is enough. Yep. And we'll get an intersection point right here. And so now we see where the three meet. And this triangle looks pretty small. And so for an estimated location, this looks pretty good. So we now know this is our estimated location. And the next step is how accurate is this estimated location. The estimation is completely based on that we're working in 1 decimal of an arc minute. So all the intersects are based on the 1 decimal, right? So that is the maximum accuracy that we have. We have the bearing, of course, as well. So that is also a certain inaccuracy that's also to only 1 digit. So what we can do is basically say, well, this is the middle point. I'm not exactly going to calculate it. The tool can do it, like it can calculate all the centers, but I'm not going to do it. I'm just going to estimate where it is by just clicking. And let's draw that as well. So we'll take this point and we'll say, okay, what would 1 nautical mile, basically what is 1 of, right? So that is what we think is the maximum distance. We'll have to zoom in again to our point. And this is roughly where we feel now is our accuracy. We can do that, however, slightly more accurate by saying, well, what if we change the length of the intercepts to what is the minimum and what is the maximum value? So in other words, we drew at the beginning, we drew this line with a distance of 14.8. What if we drew it with 14.75? Because that would round to 8, right? And the same, what would happen if we draw it by 849, which would also round to 14.8. That is now the maximum inaccuracy that we would have in the intersects. And if we start drawing that, then we can find an area that all meet the same criteria. And that's what I'm going to do next. So to summarize, so we have the estimated location, and we have an expectation that this is our accuracy. And I mentioned about the intercept, that we could vary in length so that it would still round to the same numbers. If we do that, we get the following picture with a lot of different lines. But the lines you have to pay attention to is that the brown, the blue, and the yellow, they form our estimated location, right? And they are right here, actually close to the History Museum. And that may very well be the location, right? We don't know yet. I record all this before the event. However, we see all those lines, and basically this is the maximum and this is the minimum, and you see here the values that were used, right? So we basically each time have three values that are located near the same one. So we see here the 16350, 16.4, and 16459. Those are these three lines. And then this is 11945, the 11.9 that we of course calculated with. But this one would also round to 11.9. So realistically, all the ones that match need to fall into in between those for all three combinations. And if we do that, we get to this little diamond shape where exactly anything within this diamond shape would round to the same numbers and would therefore give us the same intersect numbers. And because they're same intersect numbers and we use the same angles, they would calculate back, if you would do the puzzle backwards, to the same locations on the sextant if you're making this puzzle. So somewhere our final location will be in this location. Note that almost half of it is here, this field. I don't think the water is going to be relevant, so we're pretty safe if we start looking here. If we don't see anything happening here, we'll have to go to Broad Street and see if we see something on Broad Street that may be occurring. So that is the strategy right now for the location. Okay, so that was the last step of the Tshirt where we calculated the location and the estimated location. This is some of the reference material I used. Actually, these videos were very nice in explaining all the concepts. There's some reading material if you want to look up more specific details about the steps. And also on how to use the almanac. There's a specific series from the Vanderbilt University that talks more about how to read the almanac. Together gives you all the information that you need to fill in this navigation part. As I mentioned before, this is recorded before the event, so this is the assumptions that I go in with. It's in downtown Rome, based on the estimated location. It's the date and the time that we have to meet, and a tapestry will be rolled out. So combo lock, most likely a 4-digit one, because the 3-digit ones are very easy to crack. We'll get a tapestry with further instructions, which will bring us to a new location. Maybe through a projection, maybe to something else, maybe there's another step we need to do. We'll find out. And certainly, we think at this point the combo lock is 3211. It might be something different, we'll find out. But that is the assumption right now. Also here, there may be extra steps required. We don't know yet. That is, there's always a guess at this point in time. So I may do a follow-up video to kind of show what happened and was I right about these calculations? How correct was it? Maybe some other steps that maybe were done here that I do some corrections. But for now, this is the calculation and how to solve the pre-event Tshirt. With that, reach the end of the video. Please like and subscribe. That way you stay up to date on other videos as well. I do a lot of videos on mystery caches, how to solve mystery caches. I typically use my own. So worst case scenario, you get to know how to solve one of my puzzles. If you want to reach me, you can reach me as waterfan5 on geocaching.com. Or you can email me at geocacher.waterfan5@gmail.com. If you have any remarks, if you see something that was wrong, very well possible, then please leave a comment. Or if you just liked and appreciate it, feel free to leave a comment as well. It's highly appreciated. With that, thank you very much. Take a look at the other videos and see you in the future.